Hey everybody, and welcome to our next video in Unit 13, which we're going to focus on concentration. I'm sorry if my light is like blinking a little bit. I don't think it's getting quite enough power from my laptop to there. So I'm sorry. Hopefully it's not too distracting as you're watching this. But we've been talking about solutions, we talked about solubility, and we talked about dissolving solutes in a solvent. Usually our solvent is going to be water just because it is the universal solvent. It's the most abundant. It works very well when you're dissolving a whole bunch of different things. And you also did that PhET simulation where you started to look at concentration, and it actually told you the concentration of various solutions. So we're going to talk today about what that means. So let's talk first, or get a definition down for what concentration is. The concentration of a solution is a measure of the amount of solute that's in a particular solvent or in a solution. And we can quantify the concentration a couple of different ways, right? Sometimes you might see percents, a percentage solution. Like if you look at a peroxide solution, it says 3%. That's the concentration of that solution. It is 3% hydrogen peroxide. We don't always work with percents in chemistry, though. We tend to work with two other different units, which is what we are going to get into here today. But anyway, it's the measure of the amount of solute that's in a solvent or in a solution. And there's two ways that we can categorize solutions. They can either be very dilute or they could be relatively concentrated. So a dilute solution is when you have a relatively small amount of a solute that's dissolved in a solution. So if I have just a little bit of salt in water, that would be considered a dilute solution because there's not a lot of solute that's present. So for example, here would be an image of what a particle diagram would look like. Notice that if these red triangles are my solute, there's not very many solute particles that are present per solvent particles, and we recognize that as being relatively dilute. On the other hand, if you have a very concentrated solution, that means that you have a relatively large amount of solute that's dissolved in a solvent. So you might hear me say in the lab, be careful with that sulfuric acid, it's relatively concentrated. That means that there is a lot of acid per volume of water. So if we were to compare these images to one another, a more concentrated solution would look something like this. So notice how you have a lot more solute particles that are present in that same volume. So there is more solute particles per unit volume in the solution or in the solvent. So we can measure concentration based off of this. And there's really two different ways that chemists tend to measure the concentration of a solution. And the first way is by looking at the molarity of the solution. So the molarity, if we were to get a definition down, is the number of moles of solute that's dissolved in 1 liter of solution. And really, there's no other way to talk about it than to just get the equation down. So the molarity, which is represented by a capital letter M, I tend to underline it. That's what I've always been familiar with doing. However, you might see some textbooks or some online sources tend to italicize the capital letter M. Ultimately, it doesn't matter as long as you recognize that that is the molarity. But molarity is equal to the moles of solute that's dissolved in however many liters of solution at the very end after the solution has been made. So when you take the moles of solute and divide that by the liters of the solution, that gives you this quantitative value that we call the molarity. And it's represented, like I said, by that symbol. So if you see that I have a 3 molar hydrochloric acid solution, that means that there are 3 moles of hydrochloric acid that are dissolved per every 1 liter of solution. And the way that we usually say, like 3 molarity, we call it a molar. So that is a 3 molar solution of that. Just so you know that that's how we would express that in words. And here's just a little image that could represent that. So notice this one all the way over on the left is a relatively diluted solution, because there's not very many moles of copper 2 sulfate that's dissolved in whatever that volume is. If I add more copper 2 sulfate, I'm assuming it's 2, it's not saying, but my number of moles of solute is increasing. So the molarity of that solution is getting higher as well, until, of course, you could have a saturated solution. Just because something is concentrated does not mean it is necessarily saturated. You might have remembered when we did that reading a solubility chart, there are some substances that can dissolve barely any solute in it. So even though something could be saturated, it doesn't mean it's necessarily concentrated. It could be a relatively dilute solution, but it's also saturated. So just keep that in mind as we're progressing through, going through this unit.
So let's take a look at sample problem 5. So this one is asking, you have 3.5 liters of a solution that contains 90 grams of sodium chloride, which is just table salt. What is the molarity of that solution? So we're going to use this equation up here in order to calculate that molarity. So I first have to find what are the moles of my solute and what is the total volume of liters of that whole entire solution. So sodium chloride or salt is going to be my solute because that's what's being dissolved in this case. And I'm given 90 grams of that. So the first thing I have to do is convert 90 grams of salt to moles of salt because it's in moles of solute. Molar mass of that is 58.44 grams of NaCl is equivalent to 1 mole. And this gives me a mole value of 1.54. So that means that 90 grams of sodium chloride is equivalent to 1.54 moles of sodium chloride. Now that I have that and I'm given the liters of the solution, so that solution is 3.5 liters, all I have to do is divide those two things. So my 1.54 moles of sodium chloride divided by 3.5 liters of the solution, that's going to give me my molarity. And in this case, the molarity is 0.440. And remember, the units for this are molar. So I'm going to do a capital letter M. And then I always underlined it. That's just something that I've always done. I know I said this in the previous part. I like to underline it because there's so many M's, like so many variables for M, it's hard to keep track of them. So I like to underline the concentration ones. And that's it. Of course, there's a lot of manipulation that we can do with this particular equation. We're not going to do that here, but I just wanted you to get the general idea of how to use this equation to calculate the molarity. And I do this quite a bit. If I need to make a molar solution from a solid, I use this equation a lot. So this is a very relevant calculation that many chemists will use. So this is a very important one to know. On that note, let's go on to dilution.
Now, sometimes you might have a more concentrated solution and you have the task of making a less concentrated one. This is something I do all of the time. Not only do I make solutions from the solid solutes like you saw with the other examples, but I also perform dilutions. And a dilution is the process of preparing a less concentrated solution from a more concentrated solution. Hydrochloric acid tends to come at a concentration, I think, of about 12 or 18 molar. I don't remember which is which. I get sulfuric acid and hydrochloric confused sometimes, but I usually buy the more concentrated solution because then I could make whatever concentration of solution that I need for any labs that we would do in class. And I would do that by performing a dilution. I'm making a less concentrated solution from a more concentrated solution. And the equation looks like this. So it kind of looks like Boyle's law in a sense. The molarity of the first solution times the volume of that solution is equal to the molarity of the second solution times its volume. So let's say that I want to make 200 milliliters of a 0.1 molar solution. I would set both of those equal on one side. I need 200 milliliters of a 0.1 molar solution. And maybe I have a 3 molar solution, right? I would set that equal to my other side. And this would tell me how many milliliters of the 3 molar solution do I need to make 200 milliliters of the 0.1 molar solution. So as the molarity goes down, the volume is going to go up. So you're going to have that indirect relationship like you do with Boyle's law as you're performing a dilution. And as you can see in this image, as we go across, these particular solutions tend to get more diluted. We can tell because the solutions are becoming more clear. So that one over on the left is a very dark solution. That tends to mean it is more concentrated. There is a lot more solute that is dissolved in there. As I progress to the right, I have a lot less solute that's dissolved. So let's go ahead and try the next sample problem and do a dilution together.
So now let's do sample problem 6 using that dilution equation. So because this is on the page before, I'm just going to rewrite this. The equation is M1V1 equals M2V2. So this means that the molarity of one solution and whatever volume I need of that original molarity is going to give me some molarity of a new concentration of solution. I think this is easier to actually do a problem than it is to talk about it. So let's go ahead and try this one here. It's worth noting that your units of volume don't matter. And that's because whatever unit you have on one side is going to be the unit you have on the other side, kind of like Boyle's law. So I said that this is very similar looking to Boyle's law. As long as you're using molarity, of course, because what we would have to do this for molarity, it's a dilution. The volume units really don't matter. So this one says you are given 14.8 molar ammonia. How many milliliters of the solution is required to give 100 milliliters of a 1 molar solution? So I have 14.8 molar ammonia, and I want to know how many milliliters of this do I need to make 100 milliliters of a 1 molar solution. So this right here, let's get a highlighter. I want 100 milliliters of 1 molar ammonia. That's going to go on one side of the equation. And on the other side, I'm going to use this 14.8 molar, and I'm going to try to find what's that volume. Okay. So using that, let's go ahead and solve this. We're just going to plug everything in here. So I have 14.8 molar ammonia. And I want to know what volume of that do I need to make 1 molar solution. And I want 100 milliliters of that. So I'm going to solve this algebraically, just like you normally would, and you would find that you would need 6.76 milliliters of that more concentrated ammonia. So you would need 6.76 milliliters of the 14.8 molar solution in order to make 100 milliliters of the less concentrated one. So this right here answers this first question, how many milliliters? So if I put a number 1 next to that, this is the answer for that first one. However, there's this second question here. It says how many milliliters of water should be added to make the desired solution? So I want a solution that's 100 milliliters. 100 milliliters of solution. And if I have to add 6.76 milliliters of ammonia. So in this case, it looks like I would need to add 93.24 milliliters of water to that solution. Okay, so, or this is 2 rather, not B. So I would need to add 6.76 milliliters of the more concentrated solution to about 93.24 milliliters of water to give me 100 milliliters of the less concentrated solution. Now, this number can change, and the reason why is because if intermolecular forces come into play, a lot of times particles can actually get closer than that, and you might need to add a little more. I hope for us to do a lab so we can make a couple of solutions and kind of see what I mean there. But anyway, that's how you would perform a dilution. These are very simple problems. Again, a very relevant thing that you would do in any chemistry lab. You'd have to make your own solutions. Let's do the last section on molality.
Let's talk about the second way we can express concentration in chemistry, and that is by measuring the molality of a solution. So we have molarity, which is the most common form of expressing concentration. However, as you're going to see later, as we progress a little bit more into colligative properties, another useful way of expressing concentration is by looking at the molality of a solution. And the molality is the concentration of a solution that's expressed in moles of solute per kilogram of solvent. So they're very similar because we still have moles of solute on top. Let me just show the equation here. But in this case, molality has kilograms of solvent in the denominator portion, as opposed to molarity that had liters of solution. Why would this be? Well, that's because a lot of times concentration can change when the temperature of a solution changes. And that's because the volume of a solution can change just a little bit, not a lot, but enough that it could skew some results. So we tend to use molality as a form of concentration when we are worried about temperature being a factor, because the mass of the solvent is not going to change based on the temperature, but the volume could change. If I have a solution that's at a much higher temperature, because temperature is a measure of kinetic energy, that solution could actually take up a little bit more space. So like I said, that could skew your results a little bit. So we tend to use molality more so with colligative properties when we talk about boiling point elevation and freezing point depression in one of the later videos in this unit, which is why I wanted to show you this here. Notice that molality also has an M, but it is a lowercase m. And it is also underlined. So remember, in a textbook, you might also see that that is italicized. As long as you recognize that the lowercase m is the molality, that's really all you need to be familiar with. So on that note, let's go ahead and do the last sample problem in the notes.
So we have molality here. A solution was prepared by dissolving 17.1 grams of sucrose in 125 grams of water. Find the molal concentration. So here's my equation again. Very similar to molarity, except I have kilograms of solvent on the bottom. And remember, this is because molality is temperature independent. We could have different substances, or we could have a solution that has a certain molarity, but if the temperature changes quite a bit, that volume of the solution can change, and that affects the molarity. Not a lot, but enough that it could skew very precise calculations. So we tend to use molality when we're working with more extreme temperature conditions and not at room temperature. So sucrose again is my solute. And I have water as my solvent. It's always good to identify which is which in this case. So let's go ahead and convert my solute to moles. So 17.1 grams of sucrose, C12H22O11. And the molar mass for that is 342.94 grams, and that's per 1 mole of sucrose. So I get 0.0499 moles of sucrose. That should be an 11 right there. So now that I have that and I have the mass of my water, my solvent, all I have to do is just divide. So 0.0499 moles of sucrose divided by, just be careful because the unit is in kilograms. So a lot of times you will have to do a very quick moving of the decimal. Kilograms of water per moles of, I'll just do sucrose here rather than writing out the formula. And then your final answer should be 0.399 molal. So you would have produced a 0.399 molal solution if you had these conditions for a sugar solution. Like I said, we're going to manipulate problems like this in class. However, both equations, or all three equations, are actually quite simple. Sometimes you might be given a different variable, and it's just a matter of manipulating the equation a little bit different in order to get the desired answer. As always, if you have any questions, please let me know, and I will see you in the next video when we start talking about colligative properties. Bye.